Hi everybody, welcome to another Astronomy 102 lecture. This time we'll be talking about something called stellar evolution. Although on human timescales the stars appear to be mostly static and unchanging, all stars go through phases in their evolution. Stars are born and they eventually die. We use the term stellar evolution to describe their life cycles. Before we launch into a description of stellar life cycles, though, let me remind you of a few important points from the previous couple of lectures. First, recall that our Sun maintains a precise balance called hydrostatic equilibrium, where the inward pressure of gravitational collapse is balanced by outward pressure. In the case of ordinary stars, the source of this pressure is nuclear fusion at its core. Specifically, the conversion of hydrogen, 4 hydrogens, into helium, a helium nucleus, in the very hottest inner regions of the star. In this process, energy is released in the form of light. Recall, too, that stars come in many different flavors. Last time, Maria talked about stellar classification, which allows us to tell the temperature of a star. From hottest to coldest, we classify stars according to the scheme OBAF-GKM, or O be a fine girl or guy, kiss me, or various other clever acronyms that I hope you guys came up with. This classification is what lies along the x-axis of the Hertzsprung-Russell, or HR diagram, shown here. This diagram will be very important in this lecture, so let's take a minute to review it. Temperature increases to the left in this diagram, which is a bit untraditional. So the hottest stars are on the left and the coolest on the right. Along the y-axis, you'll find luminosity, or absolute magnitude in this case on the very left-hand axis, which is another measure of the same thing. Notice the dark strip running diagonally from the bottom right to the upper left of the diagram, labeled the main sequence. This is the region where all ordinary hydrogen-fusing stars lie. It's where our Sun is now and will remain for 90% of its total lifetime. But you may have noticed that there are labeled regions in this diagram aside from the main sequence. Our Sun will pass through some of these regions as it evolves. It will move up here, so it's here now. It'll move up here when it runs out of fuel, and eventually, it will end up here. So we'll talk about this in this lecture and the next few. So you could ask again this question of whether stars are actually static and unchanging. This diagram tells us that they aren't. All stars are born and they reach the main sequence, but they don't remain there forever. So in this lecture, we're going to talk about what we call the post-main sequence. Which is how stars move across the HR diagram as they evolve. The post-hydrogen burning phase is called the post-main sequence. 2 lectures ago, I talked about how ordinary stars turn hydrogen into helium in their cores. In this lecture, we'll discuss how all other types of atoms are made, all types of atoms other than hydrogen and helium. This process of making new atoms is generally called nucleosynthesis. In the context of discussing post-main sequence evolution, we'll also introduce the idea of stellar death and what is left over once a star is no longer a star. However, Maria will cover these stellar end states in much more detail in the next lecture. So let's begin, as we did in the last lecture, with the main sequence. Stars take a while, a few million years, to stabilize and reach the main sequence as they're forming. We'll discuss this phase of stellar birth, called the pre-main sequence, in a few lectures. Before we discuss the post-main sequence today, though, let me remind you that stars spend the majority of their lifetime, 90%, at a single spot on the HR diagram somewhere along the main sequence. A star's location along the main sequence is entirely determined by its mass, with the smallest M stars located at the bottom right and the largest O stars in the upper left of the main sequence. The mass that a star is born with also determines its lifetime. The brightest O stars, which we've compared to rock stars in the past, live fast and die young. They have a large reservoir of fuel because they're so massive, but this fuel is used up very quickly. Their main sequence phase lasts just 10 million years, a very, very short time on astronomical timescales. The smallest M stars live a much longer time, longer in fact than the current age of the universe at 13 billion years or so. We believe these stars live up to 100 billion years in total, so there's a long way to go before the very first ones that were created in the universe will evolve. Our sun is a pretty average-sized star, and so its lifetime is somewhere in the middle, about 10 billion years. And since our sun is about 4.5 billion years now, it's approximately halfway through its main sequence lifetime. So if stars on the main sequence are in hydrostatic equilibrium, driven again by pressure from hydrogen fusion, balancing gravitational collapse, then what happens when the hydrogen runs out? Well, the star will no longer be in balance, so it'll leave the main sequence. When hydrogen fusion stops, the inward and outward pressure in the star are no longer in balance. Gravity begins to dominate. So what happens to the core in this scenario? Well, as gravity wins, the star begins to contract. As the core is compressed, the atoms that make it up start to move faster. Since the motion of atoms and molecules is the definition of temperature, this means that the temperature at the core begins to go up. The dominance of gravity in a star where hydrogen fusion is no longer sufficient to support it against collapse causes it to contract and heat. Eventually, the temperature in a region surrounding the inert helium core reaches a point where hydrogen fusion can start again. It's no longer fusing at the core of the star, but now in a shell surrounding it, where the temperature used to be too cool for hydrogen fusion. Hydrogen shell burning proceeds at a higher rate than core burning. Heat builds up inside of the star and causes it to expand. As the star leaves the main sequence, it moves up and to the right in the HR diagram. Upward motion means that the luminosity is increasing, but the rightward motion means that the temperature is decreasing. How can this be the case when luminosity and temperature are proportional to one another? Well, we have to invoke the other variable in luminosity. Recall from the last lecture that the Stefan-Boltzmann law tells us that luminosity is proportional to both temperature and size. If the temperature in these stars is going down, but the luminosity is going up, then the size of these stars must be drastically increasing. Because of their cool temperatures, which make them appear red, and their extremely large sizes, these stars are called red giants. The size increases quite dramatically, in fact. When our sun becomes a red giant, which don't worry it won't for another 5 billion years or so, it will expand beyond the orbit of Mercury, and some believe even farther. Earth won't be a very great place to live when this happens, although again, it's pretty far in the future, so I wouldn't worry about it too much. So what happens to the core in this situation? As hydrogen shell burning continues, the core has nowhere to expand, and helium ash from the hydrogen burning shell is constantly raining down from the hydrogen burning shell, and increasing the density of the core. The inert helium core shrinks and heats until a helium flash occurs. The helium flash happens when the core has reached a high enough temperature to fuse helium atoms together to make carbon and oxygen. Core fusion has restarted, only this time the core is fusing helium instead of hydrogen. The star decreases a bit in luminosity at this point and also heats up, so it moves to the left in the HR diagram on a track that we call the horizontal branch. A star that's fusing helium in its core is back in hydrostatic equilibrium. Hydrogen shell burning plus helium burning at the core are together enough to balance the star against gravitational collapse. So hydrostatic equilibrium is restored. There's a precise balance between outward pressure generated by fusion and inward pressure from gravity. All stars, regardless of their mass, reach this point in their lifetime. Unlike hydrogen fusion, which lasts billions of years, helium fusion is a less efficient and higher temperature process. And the helium burning lifetime of a star is therefore much shorter, lasting only about 100 million years versus 10 billion years of hydrogen burning on the main sequence. Helium burning is only about 1% of a star's total lifetime. At the point when helium fusion ends, the next step in the life cycle of a star depends on its mass. For stars less than 8 times the mass of the Sun, the core is out of fuel. Like before, when helium fusion stops, the core will contract and heat until fusion is ignited in a shell around the core, where the temperature used to be too cool for hydrogen fusion or helium fusion to happen. In this case, there will actually be 2 shells. The one closest to the core, where the temperature is the highest, will fuse helium, and a shell beyond that at a higher radius will fuse hydrogen. At this point, the star begins to move up and to the right again in the HR diagram, cooling and drastically increasing in size. This track is called the asymptotic giant branch. So what happens here at the peak of the asymptotic giant branch when these shells also run out of fuel? Well, at this point when fusion stops entirely in the star, it's expanded so much that the outer layers simply drift away. They form beautiful rings called planetary nebula, such as this nebula, kind of uncreatively called the Ring Nebula. And here's another one. Planetary nebulae are an end product of stellar evolution. They're the lost outer layers of a burned-out star. Here's a diagram that summarizes the movement of a low-mass star through the HR diagram. The star leaves the main sequence when core hydrogen fusion stops and moves up and to the right on the HR diagram on the red giant branch, as it contracts under gravity and hydrogen fusion is ignited in a shell around the inert helium core. As hydrogen shell burning continues, the shell rains helium ash down onto the core, compressing and heating it further until at the very tip of the red giant branch, helium fusion is ignited in the core and a helium flash occurs. The star heats up and shrinks, moving down and to the left in the HR diagram on the horizontal branch. The helium burning lifetime of a star is short, and once the core runs out of fuel again, the star begins to collapse under gravity. As the star is compressed and heats, regions surrounding the core where the temperature was not originally hot enough for fusion are ignited. Those closest to the core and hottest burn helium, and a little farther out and cooler is a shell that burns hydrogen. These double shell burning stars move up and to the right again in the HR diagram, expanding and cooling and drastically increasing in size so that the luminosity shoots up. This track is called the asymptotic giant branch. Eventually, these shells too run out of fuel, and at this point, rather than collapsing, the outer layers of the star are so far away from its core that they simply drift off into space and form a planetary nebula. So the life cycle of a star, a low-mass star, goes from main sequence to various forms of red giant to a planetary nebula. But what happens to the dead core of the star? See this tiny black dot at the center here? The core of the star becomes something called a white dwarf. White dwarfs are the burnt out hydrogen and oxygen cores. White dwarfs are the burnt out carbon and oxygen cores of low mass stars. They can have as many as 1.4 times the mass of the Sun, but are concentrated into an area as small as the size of the Earth. They're very hot, dense objects, and are supported against collapse by some weird and interesting physics, which Maria will discuss next time. Very dense and small means that they don't have a lot of area to radiate, and the residual heat that's left over in the star is trapped, so they take a very long time to cool. White dwarfs stick around for a very long time. That's the last piece of the evolutionary track in this diagram. As the outer layers of the dead star drift off to become a planetary nebula, the core contracts to form a white dwarf. If we come back to this picture of the ring nebula, you might now notice this tiny blue star at the center. This is the white dwarf remnant of the star that formed the ring nebula. So here's the complete evolutionary sequence for a low-mass star. Main sequence, to red giant, to planetary nebula, to white dwarf. But what about high-mass stars? Remember we made this division between low-mass and high-mass stars? After core helium fusion stopped, the low-mass stars were out of fuel, but that's not the case for the high-mass stars. In these stars, the shell plus core fusion game can continue. Stars greater than 8 solar masses have enough gravitational force, due to their large mass, to compress their cores even further when they run out of fuel. They can ignite the burning of heavier and heavier elements in their cores and have more and more layers of shell burning. In each case, the ash of the burning level trickles down into the next shell, and ash builds up at the center of the star. These stars zigzag back and forth across the HR diagram as this happens, getting larger and smaller, hotter and colder, and fusing heavier and heavier elements in the very core. As you may have noted when we were talking about smaller mass stars, new elements are created in this process. Small stars turn hydrogen into helium, and then helium into carbon and oxygen. Large stars turn hydrogen into helium, then carbon, then oxygen, just like small stars, but they continue. They form oxygen, carbon and oxygen into neon, then magnesium, then silicon, and then iron. But it stops here. In order to understand why this process stops at iron, we need to understand why energy is released when fusion happens. So where does the energy in fusion actually come from? Let's start with hydrogen to helium fusion to understand. As you'll recall from a couple lectures ago, the process of hydrogen fusion turns 4 hydrogen nuclei, 4 protons, into a helium nucleus, which consists of 2 protons and 2 neutrons. Consider a neutral atom of helium, which has this nucleus with 2 protons and 2 neutrons plus 2 electrons to make it electrically neutral. If we add up the masses of each piece of this atom, defined in a special unit called the atomic mass unit, then the total mass of a helium atom with 2 neutrons, 2 protons, and 2 electrons should be 4.0329802 atomic mass units. If you're wondering why we list so many decimals, it's because we actually do know the masses of protons, neutrons, and electrons to this level of accuracy. If we take the actual observed mass of a neutral helium atom, it's not 4.0329802 AMU, which is what you might expect just by adding its components together. The actual mass of a helium atom is just 4.0026033 atomic mass units. This means that 0.0303769 AMU were somehow lost in the process of making a helium atom. At this point, in order to understand, we need to bring in Einstein's most famous equation. E equals mc squared. You've probably all heard this equation before, but if you thought it was something that was beyond the realm of your comprehension, you're wrong. When Einstein developed this equation, he was articulating something very simple but profound. Recall that the speed of light in a vacuum is a fundamental constant of nature and never changes. So Einstein was saying that through this equation that energy and mass are related to one another. In fact, through this equation, one could simply think of mass as a form of energy. It's another fundamental law of nature that energy and mass cannot be created or destroyed in the universe. So the missing mass from the sum of the constituents of a helium atom to its actual mass must go somewhere. And this equation tells us that the only place that it could go is into energy. To look at this another way, it requires less energy for the components of a helium atom to be bound together than for them to live separately. So when a helium nucleus is made out of its constituent parts, energy is released. We use the unit electron volt to describe energy released on atomic scales. And for this particular process, 28.3 mega electron volts are released. It sounds like a big number, but it's actually quite small. However, this is the energy released in the form of a formation of a single helium atom, and the sun fuses 620 million metric tons of hydrogen into helium in its core every second. So it adds up to be very powerful indeed. How powerful we'll leave as an exercise in class. The energy that's liberated in the course of forming an atom out of its constituent parts is called its nuclear binding energy. Here's a plot showing the value of nuclear binding energy for all of the naturally occurring elements in the periodic table. You can think of this as the energy liberated in the process of forming that nucleus, or as the amount of energy that's required to split it back up again. Hydrogen has a value of 0 because it has only a single proton in its nucleus, so there's nothing to be formed. In joining hydrogen atoms to make helium, there's a large jump in binding energy. A lot of energy is liberated in this process. The reason that lithium, beryllium, and boron are not made from helium fusion is that the nuclear binding energy is actually lower for these atoms than for helium, so no energy would be created in this process. Helium is bound into carbon and oxygen atoms. The jump in binding energy is not as large here as it was from hydrogen to helium, so this process is not as efficient as hydrogen to helium fusion. You just gain a little. You have to put in a lot of energy and achieve a very high temperature to make it happen, and not nearly as much energy is created in the process as with hydrogen fusion. So this is why stars don't fuse helium to begin with. They fuse hydrogen as long as they can because it's a much more energy efficient process. So for these heavier forms of fusion, you put a lot in and you only get a little bit out. And if you look carefully at this curve, you can see that it increases, albeit slowly, until it reaches iron, Fe, and then it slopes downward. This means that in fusing iron into anything heavier, you wouldn't release energy, you'd actually require it in order to form heavier nuclei. This means that fusion would require more energy than it would generate. And since it's not, as we say in physics, energetically favorable to do this, put more energy in than you get out, it doesn't happen. Stars will not fuse any longer once their cores become iron, no matter how big they are. So what happens? Iron's here, by the way. Once a large star has completely run out of fuel and has nothing but iron left at its core, it's impossible for fusion to continue, and there's nothing that can support the star against collapse. The star implodes under gravity, and the outer layers of the star rebound against the incompressible core and generate a massive shock wave that propagates outward, compressing the rest of the material in the star, heating it, and causing it to fuse all at once and quite explosively. This process creates many, many neutron-rich nuclei that are unstable. These nuclei release their neutrons, and these neutrons are captured quickly by other nuclei before they can decay. These neutrons decay into protons and form new elements, with a new number of protons in their nucleus, which, remember, is the definition of an element. Elements differ according to the number of protons in their nucleus. This process, called the R for rapid process of neutron capture and decay, creates more than half of the elements heavier than iron in the periodic table. If you look at this view of the periodic table, all of the blue elements, the ones that are colored blue, are created through this process of type 2 supernovae and the R process. Notice that some elements, such as Ag or gold, are entirely blue, which means that supernovae, the explosion of massive stars, are the only way to make them. That's right, all of the gold on Earth was created in a supernova. Supernovae are truly energetic events. A single supernova can be as bright as an entire galaxy, as seen in this before and after image. But their impressive brightness is not the most interesting thing about them. The massive amount of energy released in these explosions carries all of the new elements that are created in the explosion out into the universe, where they're incorporated into new generations of stars like our sun. That's right, our sun can't be a first-generation star. It couldn't have been created in the early universe, or life on Earth wouldn't exist. The carbon in the organic material that makes up your body, the oxygen and nitrogen in the air that we breathe, were all created in a post-main sequence star, a red giant. And the gold in our jewelry and uranium and plutonium in our nuclear fission reactors were created in supernovae. As the great astronomer Carl Sagan once said, "We are star stuff. The Earth and humans on it would not exist if heavy elements had not been created in earlier generations of stars. You can't have Earth without stellar evolution." To summarize, large main sequence stars, like all stars, become red giants as they run out of fuel. They're able to fuse many heavier elements than small stars, but fusion stops as iron builds up in their cores, so they can't create all elements. This is because it's not energetically favorable to fuse beyond iron. When fusion stops entirely in the shells around the iron core, the star implodes, rebounds off the core, and forms a supernova. The supernova generates both other heavy elements, and it disperses them into the galaxy where they can be incorporated into future generations. You may have noticed that the supernova here in this slide is labeled type 2. There are actually other types of supernovae that we'll talk about in future lectures. But when massive stars die, they create type 2 supernovae. Just like with the creation of a planetary nebula, there's something left over in the core after a supernova. Remember that the explosion that was created when the supernova happened was generated by the outer layers rebounding off the core. So the core itself tends to remain behind. The cores of massive stars, for reasons that Maria will explain in the next lecture, are too massive to become white dwarfs. They become neutron stars and black holes, very exotic types of matter. So here this is pictorially. Type 2 supernovae. If you want to know more about what happens after a type 2 supernova, stay tuned for the next lecture. That should leave you with plenty to think about today, so I'll stop here and summarize. In this lecture, you learned that all stars become red giants when they exhaust the hydrogen fuel at their cores. Red giants are cool, so red, and large, so giants. In fact, they're very, very large, and therefore very, very luminous. All stars zigzag across the HR diagram as they evolve after the main sequence, but eventually reach a point where they can't collapse enough to keep fusion going in their cores. Stars with masses less than 8 times the mass of the Sun stop after they've fused helium into carbon and oxygen. Their outer layers puff away from the core to become planetary nebulae, and their cores collapse to form white dwarfs. More massive stars continue fusing heavier elements, carbon, oxygen, neon, magnesium, and silicon, and create some other elements along the way. Iron, the waste product of silicon fusion, builds up at the core of the star. Iron cannot be fused into a heavier element, though, no matter how hot and dense the star gets, because it's not energetically favorable. At this point, fusion cannot continue, and the star collapses, rebounds off the core, and creates a Type II supernova. It leaves behind some exciting and exotic types of stars that we'll talk about in the next lecture. So stay tuned.